Welcome to section 2.5 called Transformation of Functions. So before we dive in, the first part of this section is going to focus on the common functions as well as the different types of transformations we'll be looking at. And then for the rest of this section, we will dive straight into examples. All right, objective number 1, recognize common functions. So below are 7 frequently encountered functions in algebra. The table shows each function's graph and lists characteristics of the function. So the first 3 here on the screen. All right, so the first one is the constant function. All right, it is a equation, f of x equals c. Its domain is going to be all real numbers. Its range is just going to be the single number c, and its constant on the interval from negative infinity. You have the identity function, right? This is where f of x equals x. Its domain and range are from negative infinity to infinity. It is increasing from negative infinity to infinity, and it's an odd function. You have the absolute value function. Its domain is from negative infinity to infinity, whereas its range is from 0 to infinity. The lowest y value is 0. So that means it's decreasing from negative infinity to 0 and increasing from 0 to infinity. And it's an even function. The next 4 functions, starting with the standard quadratic function, f of x equals x squared. Its domain is from negative infinity to infinity, and its range is from 0 to infinity, which would mean that it's decreasing from negative infinity to 0 and increasing from 0 to infinity, making it an even function. The square root function is f of x. f of x equals the square root of x. Its domain is from 0 to infinity. Its range is also from 0 to infinity, and it's increasing from 0 to infinity. And it's neither even nor odd. Then we have the standard cubic function. f of x equals x cubed. Its domain is from negative infinity to infinity, as well as its range, and it is also increasing from negative infinity to infinity, and it's odd. Then we have the cube root function, and its domain range is from negative infinity to infinity. It's increasing from negative infinity to infinity, and it's an odd function. So these are the 7 standard functions that we'll be using today and applying transformations to them. Okay. Objective 2, use vertical shifts to graph functions. So vertical shifts, we need to consider a function. So y equals f of x, one of those 7 functions we just looked at, and let c be a positive real number. If the graph shows or represents y equals f of x plus c, then we would say that the graph of f of x is being shifted c units upward. If the graph is representative of y equals f of x minus c, then we say the graph of f of x is being shifted c units downward. So in this example here, we have one of our standard functions, f of x equals x squared. And you can see here in the blue, we are adding to f of x, which is x squared. And that causes the graph to shift up 2 units. Okay. Then we have an example here in red, h of x. h of x equals x squared minus 3. Because we are subtracting 3, we are shifting our graph of f of x down 3 units. Okay, so plus c moves the graph up minus c moves the graph down. Okay, so remember, if we add or subtract f of x, it's a vertical shift up or down. Now, objective 3 focuses on horizontal shifts. So, again, we're going to let c be a positive real number. Now, horizontal shifts affect the variable. Okay, so the graph of y equals f of x plus c is the graph of f of x being shifted c units left. And the graph of y equals f of x minus c is the graph of f of x being shifted c units to the right. So horizontal shifts affect your x coordinate, whereas vertical shifts affect your y coordinate. Okay. So another thing to note here is that the direction of your shift is going to be opposite the sign. So in the vertical shift, if it was positive, we knew we went up. If it was negative, we knew we went down. Whereas in the horizontal shifts, if it's positive C, we're going in the opposite direction, so we're going to the left. And if it's negative C, we're going to the right. So remember, if we add or subtract to the variable, it's a horizontal shift to the left or right. Add is to the left, subtract is to the right. Okay. So in our example here, going back to our standard function x squared, we see here in red, we are adding 2 to the function f of x. This causes the graph to move to the left 2 units. Then for blue g of x, we are subtracting 3 from x. This causes the graph to move to the right 3 units. So we've looked at vertical shifts, we've looked at horizontal shifts. Now we're going to look at reflections. So in both of these graphs, we have different parent functions or standard functions. For the first reflection here, we're going to look at the graph of f of x equals x squared to help us understand this transformation. So the first type of reflection is reflection across the x-axis. So you would have the graph of y equals negative f of x. And this would mean that the graph of f of x is being reflected across the x-axis. So when the negative is out front of your function, you are reflecting over the x-axis. Okay, so here we have the equation f of x equals x squared. When we apply the negative outside of our function, negative x squared, we see here that all values are reflected across the x-axis. Okay, so it changes our y coordinate. Now, when we're reflected across the y-axis, we see here in our visual that our x coordinate is changing. And so the negative value is going to be applied to the variable x. So y equals f of negative x is going to be the graph of f of x reflected across the y-axis. So our parent function here is the square root function. And so we have f of x equals the square root of x. It is being defined here in blue on the left with 3 points. When we reflect it over the y-axis, we're replacing each x-coordinate with its opposite. So now we are then given the red graph here, h of x equals the square root of negative x. So reflection over the x, each y-coordinate will be the opposite, and reflection over the y, each x-coordinate will be the opposite. All right. So We looked at vertical shifts, we looked at horizontal shifts, we looked at reflection over the X and the Y. So now we're going to look at stretching and shrinking, whether vertically or horizontally. So let's start off with objective 5 using vertical stretching and shrinking. So for vertical stretching and shrinking, we need to consider a function defined by y equals f of x, and it could be any of the 7 functions we started off with. If c is greater than 1, then the graph of y equals c times f of x is the graph of f of x stretched vertically by multiplying each of its y coordinates by c. Now, if c is greater than 0 but less than 1, then the graph of y equals c times f of x is going to be the graph of f of x shrunk vertically by multiplying each of its y coordinates by c. So in our example here, we have our parent function in blue for both examples. In the first one, c is greater than 1. And when it's greater than 1, we are going to stretch our y coordinate by c. So we'll take the y coordinate and we'll multiply it by c. Now, when c is between 0 and 1 in our second visual here, we are shrinking our y coordinate, meaning it is decreasing. So now our y coordinate is being multiplied by that value. In other words, cutting it lower. Okay, so vertical stretching will result in a narrower graph, and the graph moves away from the x-axis, whereas vertical shrinking results in a wider graph and is being compressed towards the x-axis. Okay. All right. For objective 6, we're now going to look at horizontal stretching. Okay. So if c is greater than 1, then the graph of y equals f of c times x is the graph of f of x shrunk horizontally by dividing each of its x coordinates by c. Okay. If c is between 0 and 1, so greater than 0 but less than 1, then the graph of y equals f of x times c is the graph of f of x stretched horizontally by dividing each of its x coordinates by c. So looking at our two visuals here, we have the same parent function, f of x. For the first one, we have c being greater than 1. Now horizontally, the c is being applied to the variable. It's the same case in all other horizontal transformations. Now, when c is greater than 1, we are going to be dividing each of the x coordinates by the value of c. This causes the graph to move towards the y-axis. So it's being compressed towards the y-axis. Now, when we're stretching, our c value is between 0 and 1. And this is then causing a stretch, which then moves our function away from the y-axis. So that is our horizontal stretching and shrinking. Now for objective 7, we are going to focus on graphing these transformations. So here we have a summary of all the different transformations that we have discussed. The vertical shifts, the horizontal shifts, the reflection about the x-axis, the reflection about the y-axis, the vertical stretching or shrinking, and the horizontal stretching or shrinking. All of these transformations, you will need to make sure that you can identify them, whether they are in an equation or on a graph. Okay. Now, the second column here gives you direction on how to draw the graph of f for each of these transformations. And the third column here tells you the changes in the equation that are occurring. For example, if we have f of x plus c, the change in the equation would be c is being added to f of x. Therefore, on the graph, we're going to raise the graph up by c units. Or for vertical stretching, we have y equals c times f of x. So this would mean that f of x is being multiplied by c. And on the graph, we would multiply each y coordinate by c, which will cause a vertical stretch of the graph of f. Now, a function involving more than one transformation can be graphed by performing transformations in the following order. So you'll first start off with the horizontal shift, then you will stretch or shrink, then you will apply the reflecting over the x-axis or the y-axis, and then you would apply the vertical shifting. Remember, for more than one transformation, remember the order HSRV. Horizontal, stretch or shrink, reflect, vertical shift. All right, now let's go through some problems. So for problems 1 through 3, we're going to use the graph of f of x that is provided for us, and then we're going to graph each function g. Okay? So in our example here, let's get my pen. All right, we have g of x equals f of x plus 1. Now we can see right off the bat that we are adding 1 to f of x. So this means we have a vertical shift of 1 unit upward. So every value in our function f of x, or every point, sorry, is going to be shifted up 1 unit. Okay, so this is going to affect the y coordinate. So we had negative 2, 2, so now our point is going to be negative 2, 3. Then we had 0, 2, so now we'll have 0, 3. We had 2, 2, so now we'll have 2, 3. And then we can connect our dots. Okay. Let's add our points so we have something to review. All right, and then choose it. Okay, so that's our first transformation. Let's do the next one. G of x equals f of x minus 1 minus 2. So now we have two transformations occurring here to f of x. We have subtraction of 1 being applied to the x, and then we have a negative 2 on the outside, which will apply to the y. So our first transformation, the minus 1, is going to be a horizontal shift 1 unit to the right, and then the minus 2 will be a vertical shift 2 units down. So when we take our points, we're first going to apply the horizontal shift, and then we'll apply the vertical shift. Okay, so we'll take the point negative 2, 2, right? Now we know for this point, we have a horizontal shift 1 unit to the right. So 1 unit to the right would land us at -1, 2. Okay, but we know that's not our final point because we have another transformation. Okay? Now the next transformation is a vertical shift 2 units down. So I'm going to take this point, I'm going to go down 2 units, and I land here at -1, 0. Okay? All right. So now let's take the next point, which is 0, 2. 0, 2, I now have a horizontal shift 1 unit to the right. So that will land me right here, 1 unit to the right. Then I want to go 2 units down, 1, 2. So I'll land right here at 1, 0. Okay. Then we'll take the next point, 2, 2, 1 unit to the right, which will land me here, 2 units down. Boom, boom. So I'll land here at 3, 0. Okay. So here I have 1, 0, and here I have 3. And I can now connect maps. All right. Next example, g of x equals negative f of x plus 3. So we have a transformation right here and a transformation right here. So for the negative, we know that we are going to have a reflection across the x-axis. For the plus 3, we know that's a vertical shift, 3 units upward. Okay, so let's take our first point, -2, 2. Okay, we have a reflection across the x-axis. So if we're reflecting across the x-axis, we now are going to take this point, -2, 2, and we're going to move it to the bottom part of the x-axis. So what's changing? Our y-coordinate. So we go from -2, 2 to -2, -2. Okay? Now we want a vertical shift 3 units. So now we'll go up 3, 1, 2, 3, and we land at -2, -1. Oh, sorry, not -1, +1. -2, 1. Okay. Then continuing on with our pattern, 0, 2, when reflected across the x-axis would get us 0, -2, then moving up 3 units would get us the point 0, 1. Then 2, 2, reflecting across the x-axis would get us 2, -2, up 3 units, we get 2, 1. And you connect the dots. Okay. Act to check your answers with the ones that will be presented here on the screen. When you get to problem 19, please come back and we will walk through the last 2 problems together. Happy transforming! 20. All right. I hope you had a good time transforming and you were able to check your answers with what was presented here on the screen. For our last two problems, or three, it's kind of a 2-for-1. For problems 19 through 20, functions f and g are graphed in the same rectangular coordinate system. If g is obtained from f through a sequence of transformations, find an equation for g. So for 19 and 20, you were given two sets of graphs, and one of them is your f of x, and one of them is your g of x. For problem 21, it's asking us to make a table of the transformations that are occurring in problems 19 and 20. So we're just going to do them together. All right. So let's start off with 19. We have our standard parent function here, f of x equals x squared, and we have our function g of x. Hint, hint, you might have something similar to this on an upcoming assessment. So the first thing we want to do to help us identify the equation is we want to list the transformations that are occurring in the graph. What has changed? Well, the first thing that I noticed right off the bat is that some sort of reflection has happened because my x squared was looking up and now it's looking down. Okay. It was happy and now it's sad. And that reflection happened over the x-axis. So I know that there's a reflection over the x-axis. So let's write that down. Okay, so 19, we're going to have a reflection across the x-axis. In addition to that, my vertex is at 0, 0 in my standard function here. Right, it's at 0, 0, but now it's at -4, 0. So that means there had to be some sort of shift that took it from 0 to -4. It's still on the x-axis, which means that my y is still 0. It's the x that changed from 0 to -4. Therefore, I know I had a horizontal shift. Now my horizontal shift is going to be to the left 4 units. Okay. Now, I don't see any other changes that occur in my graph, so I believe that I have all of the transformations. Okay, so now I need to write the equation of g of x, because that's what problem 19 is asking us to do. So to write the equation of g of x, I'm first going to start off with my parent function here, x squared. Now I need to apply the transformations. Well, if I am being reflected across the x-axis, I know I'm going to have a negative on the outside of f of x. Okay? If I am applying a horizontal shift, I know that's going to affect the x coordinate. Okay? So that means that something is going to be applied to x. Now, I'm going left 4 units. That is being represented by the opposite side. So left 4 units would be a -4, but in my equation, I'm going to have a +4. So g of x is going to be equal to negative quantity x plus 4 squared. So that's me using the graph to pull the transformations to then create my equation for g of x. All right, let's do the next one. All right, problem 20. we have our f of x function, which is the square root parent function, square root of x, and we need to find the equation for g of x. But to help us find the equation for g of x, we need to first list out our transformations. Okay? So what is occurring? What is happening? What has changed from f of x to g of x? Well, the first thing, again, that I noticed is that my graph is upside down. Okay, so again, that means some sort of reflection is occurring. That's the first thing that my eyes see, is that it's upside down. So for number 20 here, we have a reflection across the x-axis. Okay. Now, we also notice that there is some sort of shift because, again, my initial point was 0, 0, and now it's the point 2, 2. So not only is there a vertical shift, but there is also a horizontal shift. So my graph is moving up to and it's moving to the right too. So there's a shift that's occurring to the y and to the x. So let's first start with our horizontal shift. So our horizontal shift is going to be to the right, and we go to the right 2 units. Then we will apply our vertical shift, and our vertical shift is moving our graph up 2 units. So that means we're going to have 2 values in our equation that apply to both of these shifts. So let's find g of x. Okay. So we know that there's going to be a reflection across the x-axis. So there's going to be a negative on the outside of my parent function. Now we have a horizontal shift. Horizontal shift affects the variable. So that's with or within the square root itself. And we have a horizontal shift of 2 units, so it's positive. So in our function, it's going to be the opposite sign, so that would be -2. And then we have a vertical shift that affects the y, so that's on the outside of our parent function, so that would be a +2. So our final equation is going to be g of x equals negative square root x minus 2 plus 2. Okay, so again, we identified our transformations and then we use that to help us write our equation. All right, and that concludes section 2.5.